Good morning, everyone. We will be starting the webinar, Loop Tuning is the last thing you do, in 1 minute. Okay, thank you very much. My name is 𝗬𝗓𝗦𝗬𝗕𝗏. Welcome to Lakeside's series of webinars. And I'll be talking about loop tuning. It's the last thing you do. It's the first of 10 episodes that we're going to be doing. Bit of guidelines. This is obviously it's a new world, a little bit different. So a bit of guidelines regarding this presentation. First of all, your microphones are off, so you will just to make sure we want to control the talk traffic. If you do have questions, you can type in your questions on the Q&A box. You should have that on the side. You can also chat with me privately. Your questions, you can type in your questions anytime you want during the presentation. This presentation should be between 45 and 60 minutes long. At the end, I will read your question. However, all your questions will be anonymous. So I will not say this person from that company asked me this question. I will not do that. I will just repeat the question and answer the question as well. And if there's not enough time to answer all the questions at the end, you're more than welcome to contact me directly. This is my email address and so forth, and my cell phone number. So email is probably the best bet to get hold of me. This is, like I said, a series of 10 webinars that are scheduled throughout 2021. They'll be once a month, except for the summer months. That might be skipping a month or two. So this is the first one. Loop tuning is the last thing you do, and then we're going to talk more about specific aspects of process control and control loop tuning and optimization. The next one in March is going to be the P, the I, and the D, and what do they do? Talk about noise and dampening that we tend to use on noisy signals. Talk about control valves. We're going to talk about valve hysteresis, backlash sizing, CV curves, flow curves, nonlinear valves, and so forth. We'll talk about level control and how perhaps level controllers, if they're not tuned properly, can actually disturb upstream and downstream processes, and how maybe what happens when we don't tune properly. Characterizers. Some valves are maybe not very linear. I'll go through an example. Now, incidentally, from number 2 to number 10, actually, webinars all have an interactive component. I actually built a simulation, so therefore you can we'll be able to not just straight lecturing, but I will actually demonstrate some of the ideas as well. Back to number 7. Adaptive control. Obviously, if processes changed significantly, we may need to have an online changing of our tuning as we go along. Feed forward control, split range control, and then dead time compensators. So I hope to see you there. They'll be, like I said, anywhere between 30 to 60 minutes long, typically around the middle of the month of each month. This session is being recorded. So if you kind of have to leave early or whatever, you can. We will be emailing you a video of this presentation within the next day or so. A little bit of a safety moment. My wife and I both we own a trailer and something called 𝗪𝗧𝗔𝗬. And let me get my little pointer here. So this is 𝗪𝗧𝗔𝗬 right here, and this is Lake Ontario, and all this area here is actually Prince Edward County. Fabulous area, you know, if you like wineries and breweries and good food and all that. So it's an excellent place. We love it there. And you can see here on our boat with our dog. And then, but once a year, my brothers and I, we get together to do a quote unquote fishing trip. And yes, you could probably see where the safety moment's going. So we go to a fishing trip, and yes, we do actually do some fishing occasionally. And so one day, a couple of years ago, I was in charge of cooking the bacon. So I opened up the package of bacon with a knife, put the bacon in the frying pan, put the package on the side, open up a second package of bacon, open it up with my knife, put it in the pan, and then put the package on the side, put the knife on top of the packages. I fluff up the bacon and say, well, that's a lot of bacon. That's going to be really good. And I picked up the packages and I forgot about the knife. And so the knife fell. So yeah, it fell on my foot and 2 stitches. Nothing major happened, but so beware of bacon. But on the more serious side, though, I'm not sure exactly where you're all living right now. I'm broadcasting from the world headquarters of Lakeside Process Controls in Mississauga, and it is snowing today. So be careful. I know we all say this, but just be. It's not so much that the acceleration. If you have 4-wheel drive, you're okay to accelerate. But we all have the same amount. The laws of physics all apply the same, whether you have 4-wheel drive or not, on the stopping side. So always make sure that you give yourself a lot of room with the car in front of you to make sure that there's nothing bad happens. So just be careful out there. A little bit about Lakeside. We deal with all sorts of different industries. Our territory that allows us to, we exposes us to a lot of industries here. I've worked on all of these industries, probably with the exception of alternative energy. These are a lot of the products. I mean, we are the Emerson Impact Partner for all the products and services. We have control systems, safety controls, valves, measurement, analytical. We also do project services, life cycle, educational services. I do teach courses. We'll talk about that later on, consulting. So we do a lot of this stuff here. So just so you're aware about Lakeside and what we do. Our territory extends from all of Manitoba all the way across to just this side of Kingston. And we actually even have a little bit of Nunavut as well. So head office is in Mississauga. We have offices in Sarnia. We have offices and manufacturing facilities in Guelph. We have an office in Sudbury, Port Elgin, Thunder Bay, and Winnipeg. And we are an employee-owned company. There's a bit of all these different divisions. They used to be separate companies, but now they're all divisions. Lakeside, obviously. Arctic Combustion deals with border controls, and we have G1 technicians to service burners and so forth. DAC, Valve Automation Center, is a on-off control manufacturing facility as well, and we do own part of Lakeside Gas Services, which does a lot of the above ground work for like gas metering and so forth. For, if I'm not mistaken, I believe it is Enbridge and or Union Gas, and also we do service work also in Kitchener area, and I'm sure I'm forgetting a few more things. And we are one of the platinum members for Best Managed Companies. A little bit about myself. Yes, I do have over 30 years experience, and maybe at the end I'll turn my camera on. You'll see that my hair does not look like that. I got my COVID haircut going on. I am the process optimization specialist for Lakeside, and I do go in the field and do control loop. I do control loop optimization, loop tuning, troubleshooting for customers at their various sites. And I also do involved with model predictive control, advanced controls, and neural net applications. We also do DCS alarm management services as well. Anyone who's done a DCS projects probably will agree that the DCS alarm portion of a DCS project is probably the red-headed stepchild of the project itself. We don't really pay attention to it until the very end, and when we just arbitrarily set all the high alarms at 80% and the high alarms at 90%, and off we go. And then when we start up, we have the alarm banners full of nuisance alarms. So what we try to do is we're trying to make the alarms relevant as opposed to eliminate an alarm. We want to make the alarms relevant, because if you have an alarm full of banner full of alarms, what happens is when you get a true alarm, 2 things happen. The operator gets desensitized, and B, we will miss that alarm, and that's when bad things happen. And then after that, we can talk about dynamic or alarm rationalization, where if a pump trips, do not alarm a low flow, do not alarm a low pressure, because they are redundant. So again, we want to make alarms relevant as opposed to eliminating them. And that is not a stock picture. That is an actual picture we took at a customer site. where they wanted to silence an alarm that was kept on going off, so they use a steak knife. I do have a couple of individuals that kind of help me out once in a while. Andrew Poyton has actually over 12 years. Andrew does a fantastic job. He got himself promoted, so I don't have access to him as much as I would like. And Dean is also part of my supporting cast as well. And I do teach courses, basic instrumentation for operations. The next open course for that course is going to be March 24th online. Process Control Techniques 1, or AKA Loop Tuning 1, is going to be, I believe, at the end of March. If you go to our website, you can actually see where these courses are scheduled. And we have the continuation Process Control Techniques 2, which is a continuation, deals with more advanced subjects. And I do have a blog on our website, kind of lighter reading, so you can go to our website and read those. Like I said, they're not dry technical. I try to make them a bit more humorous, but there is a model. There is a sort of a I can't. There is a moral to the story. That's exactly the word I was looking for. The Unusual Suspect is kind of funny, actually. Anybody ever recall the detective series Columbo is kind of written in that fashion? So let's talk about this. Let's talk about loop tuning as the last thing you do. So when I go to site, and could be a dog food site, could be a nuclear power plant, could be a power plant, could be a pulp mill, it could be anything. First thing I need to understand is the process. So I need to understand, what are we doing? Let's walk it down. I need to look at the pumps. I'll look at the piping. I want to look at the tanks, look at the heat exchangers, compressors, blowers, all that. I need to understand that to get a good feel as to actually what I'm dealing with. Because if we don't design a process properly, it's going to have a very difficult time trying to control it. Control strategy, control philosophy. How are we controlling this? Do we have 15 pressure controls on one header, let's say? Do we have feed-forward control? Do we need maybe more advanced control? All that, if we don't design a control philosophy properly, we're not going to be able to control. It's going to have a direct negative impact on our ability to tune. Instrumentation. Obviously, on one side of the equation, you got to have the right instrument properly specified, installed, and maintained. SIM. So obviously, we have to make sure that when we design a process and that the instrumentation is properly installed. Don't install a bag meter, let's say, flange it to an elbow. That's not a good idea. Don't put your pH transmitter in another building, which I actually have seen. So don't do that. So make sure that we get the most value and we design our instrumentation so therefore we get the maximum value. On the other side of the equation, on the control valve side, we want to make sure that the valves are properly sized, they're dynamic, and they're precise. If we falter any one of those, that will have a direct negative consequence on our loop tuning. And finally, loop tuning. It is the last thing you do, and I've always approached this from the bottom-up approach. Unfortunately, though, sometimes what happens is that people say, well, I know that as I mentioned before, my pH meter is located in another building, and instead of having 20 seconds of time delay, I have 2 minutes and 20 seconds of time delay. But can you tune that for me? And odds are, yeah, maybe I can, but I'm not going to get very, very good results because of the fact that I got so much time delay. Another thing, let's say my valve is oversized, or my valve actually is sticking for 3%. But can you tune that out for me? And the answer is, I'm probably going to make it worse in automatic than on manual. So what we're going to do is that we're going to go through each layer, and we're going to talk about how, and give you a quick example as to how each of these layers affect loop tuning. Let's talk about process design. So in this example here, we got our pH controller here, and we got our tanks. And so we're going to control our pH here by inserting caustic into the tank itself. So from a mass balance or energy balance point of view, that seems fine. However, what we're going to lose out on is the fact that now we're going to have a long mixing time constant within the tank itself, and then a very long time delay from the moment I actually add caustic or remove caustic until the moment I actually measure it. So I got to have very slow process to deal with, and how fast your process reacts will dictate how fast you can tune it. Or conversely, how fast I can tune my control loop is directly dependent on how fast my process is. So here's sort of an example here, simulated example on a step change, because when I tune a control loop, I do a bump test. So the blue line is the command signal to the valve itself, and then the yellow line is the actual pH measurement. And you can see here, there's a very long time delay and a very slow response. Slow process means slow tuning. So instead of that, why don't we just tune a control loop? Why don't we control our pH by adding caustic after the valve, after the pump itself? So we avoid the slow mixing. We do have a static mixer there, and we have shorter time delay. So we should have better control. Obviously here we do need some time delay, because in this example here, because pH, a chemical neutralization has to happen. You can't measure pH instantaneously. But let's keep that measurement as close as possible, so therefore we keep that time delay as short as we can. So here's a quick example here of our bump test, and you can see I have a very shorter time delay and a quicker response on my process. Quicker process means I am able to tune it faster if I need to. So another example here of process-related issues. This is actually a real live example here. I was working on a very large boiler, and the boiler eventually was having some issues. So they asked me to look into it. And so what you're seeing there at the bottom is Xscale, the command signal to the valve itself. And what you're seeing on the y-axis is the actual boiler feed water flow. And so this was actually measured, collected on December 17th in 2018. So then I looked at it in March. And so if I flip back and forth, you can see it's sort of the curve is actually getting a little bit lower. And then after that, I measured it again in May. And what happened, so if I go back and forth, you can see that the pump curve is, this is my technical term, is wilting. So the pump is actually wearing out. So these pumps, these are not a very off-the-shelf pump. This is a pump that takes over probably 52-week delivery time, like a full year delivery time. So in the interim, what was happening is that because of the pump was wearing out, I could tune it down in this part here, but it would be too slow here, and I could tune it here, but it'd be unstable down here. So I needed something to actually be able to compensate for this nonlinear flow curve response. Here's here's the pump curve. That in this case, you got the flow versus pressure, and you can see here based on as this was back in November, and then later on in May, you can actually see how the pump curve actually drops. So what I ended up doing is developing a characterizer. And so yes, we are going to talk about characterizers in a future webinar. But what we're trying to do here is that to compensate this flow curve, we put a characterizer between the PID controller and the analog output in order to linearize the flow response. And so what it does, it still doesn't compensate for the fact that the pump is wearing out, and it's not going to get any better. But at least now we're able to have at least stable control over a wide operating conditions of the boiler feeder water pump itself. Control strategy. No loop is an island unto itself. So when we tune a controller, you can tune a control loop, but you always got to consider its role in its interactions with other control loops. So you really can't just tune a loop. You got to consider its effect on other control loops itself. So let's go back to our example here. So we got a pH controller, and it's going to, and I've seen this before. In this example here, we're going to use both valves. And what we're going to do is that we're going to control pH by modulating both valves at the same time. Yes, I have seen this before. And what that does is that it's not a very good idea, because now we're mixing slow and fast dynamics. So fast dynamics from this valve here and the slow dynamics of this valve here. Makes for very, very strange, and it's not going to be very good. You can see here the effect of the first valve, and then we see the effect of the second valve. And it makes for very weird dynamics. And you can't tune this very well because you get two responses happening at the same time. A better way to do this is to use a mid-range strategy, not split range, mid-range strategy. So what this means is that this actual valve here typically is going to be smaller. Let's say it could be a 2-inch valve, could be little brother. And then this one here could be a 4-inch ball valve. Let's say we'll call that one big brother. So what we're going to do is that we're going to control our pH using the little valve, little brother. Everything's good. We got all the good stuff happening, short time delay, no mixing dynamics. We're all happy. Everything's good, except that little brother sometimes can get into trouble. So little brother can be opening up to, say, maybe 50, 60, 70, 80% open, and we might run out of room. So now we need help from big brother. So what big brother is going to do is that he's going to look at the position of little brother. And so as little brother gets into trouble, 70, 80% open, what big brother is going to do is that he's going to open up very slowly, and eventually he's going to bring little brother back down into a controllable, the sweet spot of between 40 and 50%. And the opposite can happen as well. If little brother starts to decrease to 20 or 15%, big brother will slowly close the valve to bring little brother back up to speed. So there's an example there of mid-range strategy. Instrumentation, seeing is believing. So let's look at it from 2 points of views here. So 2 points of view. So a lot of times I have the Lakeside tuning index that I've developed, and we'll talk about this a little bit later on, but I also look at excessive PV filtering and all the PID blocks. And a lot of times, so when we use dampening, it's there to remove the noise, and I'm putting air quotes out there because obviously if we choose to put some dampening, is the noise gone? And the answer is no. It is not gone. It is still there. We just choose not to see it. And there's a price to be paid for that, because the more dampening we put in, the slower we actually slow down our process. So therefore, and the more we slow down our process, the more we need to slow down our tuning. Not a good idea. So what we should do, so here's an example here of different types of dampening there. So you can see here at 10 seconds, the noise is gone, but the process reacts slower. And at 30 seconds, obviously the process is very clean, but responds very, very slow. One of the things I also want to emphasize here is that when we do put a lot of dampening, as I probably mentioned, it probably indicates a measurement problem. So a measurement problem. So again, I talked about having a mag meter flanged to an elbow, and I've actually seen that. And so therefore, they actually put a lot of dampening at the transmitter in order to mask the fact that we messed up our process design. And this is what happens sometimes when process people may or may not fully understand the requirements of instrumentation. If we don't design our process, you can just see the piping person, the process person say, what kind of gap do you need for your mag meter? And you answer the phone, you say, well, I probably need maybe 33 centimeter gap, and that way I can put it in there. And then lo and behold, you walk up there with your mag meter, and you see your gap, it is flanged right to the elbow, and therefore that's where you got to put it in. Last chance at good control. So on the other side of the equation, we got control valves. And control valves is obviously very critical to good control. And I can't emphasize this enough. Precise control is equal good control. So we need the valve to be precise, dynamic, and properly sized. Now, control valves do suffer from two major diseases. One's called backlash or hysteresis. It is the terms are interchangeable, and the other one is stiction. So how do I detect valve backlash? So usually what I do is that when I walk up the control loop, first thing I do is I want to test the precision. I will do 1% bumps. Now, two reasons why I want to test the precision of the valve, but at the same time, I don't know I don't know if that valve is oversized, undersized, and I don't want to disturb the process more than I need to. So I do 1% bump test. And you can see here, I go up 1%, flow tracks, up 1%, the flow tracks, up 1%, flow tracks. And then I decrease by 1% and the flow did not change. That means I lost something on the direction. So backlash is due to mechanical slop, mechanical looseness within the valve assembly itself. Afterwards, I do subsequent bumps, and now I've taken up all the slack, and I get the full change. So I do actually have a video here that I want to show you. So just bear with me for a minute. Bear with me. So there, okay, so let me pause this for a minute here. So what you're seeing here is on the right-hand side is the valve stem going into the valve itself. On the left-hand side is the actuator, and beyond, further on the left, is the positioner itself. Now, the two tie wraps you see there are just a rotary motion detector that I installed, and it's patent pending, so you're not allowed to use that invention. What I want you to do is pay attention a little bit, and then you hear me talk in the background. I actually shot this video. Pay attention to the motion of these two tie wraps. So you see they're moving up and moving together. Now pay attention to the left one.
Backlash is taken up.
Now the valve's moving.
Now it's going to go the other way before it actually engages.
So it engages. So you see it had to move up. I estimate there probably probably 5 or 6%, at least, for 5 or 6 degrees, at least, before it mechanically engaged on the other side. So you can see here, very, very typical case of hysteresis right there. And this was controlling a pretty high throughput tank, a standpipe, and so they would actually occasionally trip on high or low levels. Obviously, this was a direct culprit here. So this is actually kind of funny here. So I was at site a few weeks ago, and this was actually a burner control valve, and we knew that it had a fair bit of backlash. So as an interim solution, you can see the bungee cords we put there to try to take up the slack. But really, just kidding. Don't go ahead and put bungee cords on your valves and anything like that. Fix the problem at the source. We just needed that to validate some of our process, but obviously the customer needed to fix that problem. Stiction, static friction. So that's when valves are sticking. They can have a lot of friction. It could be within the positioner. It could actually be between the actuator and the valve body, the packing itself. And here it doesn't want to move for small changes. It seems like we got to make a bit of a change, and finally, okay, now it's going to move a bit more change. Now it's not moving. We got to put a bit more, and then finally, bang, and let's go. And so what happens is that these kind of valves, sticky valves, stiction, valves that hunt, those are all terms that you probably heard before. So, and I actually have another video here that I can share with you. Just bear with me. So there we go. So here we go. So
4 milliamps.
So just pause it here. So here we have a pretty large ball valve, and it's on a skid. So it's actually, you can tell it's been in service for a bit. We took it out, and we were documenting the dynamic performance of this control valve because this actually was a brand new paper mill, and they're actually having control valve issues all around because some of the control valves were not really up to par what they really should be doing. So we hooked up the air to the actuator and the positioner, and we actually had a 4-20 calibrator hooked up to the positioner, and we're slowly stroking the valve open and close. You can see here it's a ball valve, and obviously you can see it, some of the quality doesn't look a very good ball valve here because you can see some of the scoring going on here. So here we're opening up the valve itself. As we're opening up the valve, and really as we're opening it up, we should be seeing a nice gradual opening. And you can tell here, as we're opening it up, this is not happening. is actually we're having a lot of jerky motion because there's a lot of friction within the valve itself. So you can see right there as it opens up. So I'll let it go a little bit longer. There you go. So you see all these jerky motions, and what that was doing, the valves were actually hunting, and therefore causing disturbances in the process itself. So we actually ended up getting some money back from the valve manufacturer, believe it or not, because of the poor workmanship. So let's talk about this here. So here I actually have 1% step changes, and I would just a bit of a quiz there. So, and maybe I should probably put that as a poll, but it's too late now. Is this backlash or is this stiction? So you can see here, increase, 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 and then I've got a change in my flow, and I keep on going the same direction, and no more change until a certain amount. So if you guessed, little drum roll there, if you guess stiction, you are correct. You are correct. And here you can actually, this is a telltale sign. It's one of the things that I do when I go into control room and I look at the trends. I look for this kind of pattern. And when I start seeing a triangular pattern on the output and what I call a shark fin pattern on your PV, that's a good indicator that your valve is probably sticking by almost the amplitude of that triangular pattern. So how much is too much? So when I first started doing this back in the late 80s with a company called 𝗦𝗘𝗘, if I saw 1% precision, I was actually a very, very happy camper. Very happy camper. Nowadays, I expect 0.5% precision. That means if I open up the valve 0.5%, I want to see it move or feel it move, and close it, well, 0.5%, I want to see it move as well. So that's what I expect nowadays. 1/3, if you have control-related issues, 1/3 of your control-related issues probably involve the control valve itself as well. And really, there's no tuning that can compensate for a bad valve. As a matter of fact, probably going to make it worse in automatic. So don't try to build, don't be cute, don't try to build backlash and stiction compensators in your software or anything like that. People still think they can do that. Fix the problem at the source. And really, at the end of the day, our valve should be at least 1% precise, if not better. Let's talk about valve sizing. So because valve sizing matters, right? So when you order a control valve from us, you can call up one of our application engineers, and they'll ask you lots and lots of questions as to, to be able to size, properly specify and size your control valve. They ask you min flow, normal flow, max flow, type of fluid, gas, viscosity, all these things to make the pressure, inlet pressure, outlet pressure, all these things to make sure that the valve is properly sized. All very, very important points. When I look at valve sizing, I look at it from a control perspective on how much of an effect a 1% change on the valve causes onto my PV. Now, in my PV, I talk about the universal language of percent of span. So a 1% change will actually, of course, for properly designed control loop, should change the process between 0.5 and 2% of span. Now, sometimes, though, that's known as the process gain. Nothing to do with the controller gain here. Call it process gain. I like to call it the process sensitivity, because that way we don't get confused with the word gain at all. A lot of times, though, what happens is that I do a 1% change and I get a 3% change in my process, a 4%, a 5% change in my process. And that's a problem, because now if I have a seemingly small problem on my output, on my valve, gets translated into a large problem onto my PV. And that's what the problem is when we start actually oversizing our control valve, which is probably the case here, is that small problems translates into big problems onto our PV. That's why we need to oversize our control valves. One last thing, if your control valve spends most of its life 25% open or less, that's another sign your valve is oversized as well. And we also have to understand, and we talk about this on the control valve part of my webinar, in probably 2 or 3 webinars, about how your process sensitivity will change over the opening of the valve based on the type of valve as well. And then you can start falling into using characterizers and so forth. And if you want some more information about this, there is an actual valve spec. 𝗦𝗡𝗙 is now actually owned by Emerson, but when I was working for them, we're an independent company, and that was part of actually developing this control valve specification that outlines all the anything from between the valve size, valve sizing, valve precision, and dynamic response. So it's still actually very relevant today. So let's look at some examples here. And now what I'm going to do here, I'm going to switch to my pen right here. So let's look at a few examples here of bump tests that I've done and how we can determine what's going on here. So in this example here, the red line is actually the output command to the valve, and the green line is the flow signal. So here, these are 1% bumps here, here, and here. This one's a little bit bigger. I probably was trying to round up the output. So in this example here, you can see I did a 1% bump, 1% up, 1% up, and then I did a 1% back down. And you can see here that the flow came back to where it started from. So in this example here, we have pretty much negligible or no backlash at all. And if we have any stiction, it's going to be less than 1%. So all in all, this is actually a very good bump test, a very good valve. Now, in this example here, the yellow line is the output command to the valve, and the purplish, pinkish, whatever color you want to talk here is the actual flow signal. Now, this is an interesting story. First of all, you can see here the telltale sign of the triangular pattern on the output. So obviously, we're dealing maybe with some sort of backlash or stiction here. Now, the interesting part of this is that we were trying to mechanically find problems with this valve, and every time we tested it, we couldn't find any real mechanical problems with it until we started putting a heart communicator onto the positioner. It was a smart positioner. Smart is equal to heart. And then we went through all the parameters, and we found this one obscure parameter within the positioner in software called deadband. Now, deadband was set to auto. And so we didn't know what that value was, but obviously deadband was set to some high value because you can see here 1, 2, 3, 4, 5% before we got a change in our flow. So it was a very significant imprecision. So what we did, we could actually set this deadband value in software through AMS or through a heart communicator, and we put it in manual, and then we set the value to, I think it was like 0.5%. And then lo and behold, the valve problems all went away. So in this example here, it actually went away. It was actually nothing mechanical. It was actually a software issue. So we got to be careful about that. Here's another example here where I did some significant step changes, and finally the valve would move. And then finally I actually went down 10% before I would actually see a change in my flow in this example here. 10% backlash. So in this example here was actually some looseness within the valve position feedback. Another one here, an interesting one here. You can see I did, every time I would do up bumps, going up, up, up here, flow wouldn't change. But if I did a down bump, I would see a significant change in my flow. But every time I went back up, okay, it seemed to have a hard time. And I think this one here, it actually had a leaky, the diaphragm was leaking. So therefore, it was easy to go in one direction, but it actually had a hard time going in the opposite direction because there was an air leak in the diaphragm. Which brings us to loop tuning. So a lot of time, we can tune loops, and most people tune loops. The most popular tuning method out there is obviously tune by feel. And you can read up on tuning. There's probably an article published probably every minute on the optimal tuning method and optimal this and optimal that. And there's probably some tuning tools out there which are all fine. But at the end of the day, we should probably asking ourselves, I always say let's start with the end in mind. Given this role of this control loop and its interactions with all the other control loops around it, how do I want my controller to respond? Then will I decide how am I going to tune it to achieve that response? And so I think a lot of times we've been looking at this kind of backwards. So let's talk about this. Anybody who's had any kind of tuning any kind of tuning experience or tuning training, or at colleges, universities, and all that, all probably remember Ziegler-Nichols quarter amplitude decay type tuning, where the idea is that when you tune your control loop, following a set point change, the PV will come up, and go right by the set point and go hello, and probably overshoot it. And then each subsequent overshoot will actually be 1/4 the height of the previous. So it's not a very deterministic, it's not a very good type of tuning method, because it's an underdamped response. That means it has a natural resonant frequency. It's not very robust tuning as well, because the only constant in life is change. So that's a Buddhist principle. So the same thing in process control. We know that our process will change, and we know that the tuning must match our process. So we, short of retuning a process for every possible different conditions, be it summer, winter, different production rates, different grades, or even just be based on the type of process itself, we must build some robustness, some ability of our control to remain stable, even though our process may change over a period of time. So that's what robustness means. And Ziegler-Nichols is not a very robust type of tuning. The tuning that I teach, and I'm sure some of you probably already know this, is that I teach lambda tuning. And where, in this example here, I want to have an overdamp response. And obviously, I can choose how fast my controller responds by specifying lambda. Now, obviously, limits do apply. I can't just specify any kind of lambdas. It has to be in relation to the process itself. But I can then specify, I want my PV to reach set point in 60 seconds, because that way it will match another flow going to the tank that I want to keep on ratioing, make sure constant ratio, and that flow will reach set point in 60 seconds. They'll both have the same dynamics. So I can do that. So more facts about loop tuning. Now, as I mentioned before, I've developed a Lakeside tuning index where I've actually examined almost up to 5,000 PID blocks. And 1 in 5 loops I have characterized. So I look at all the tuning, and based on the type of control loop, I will actually characterize it as a suspect, questionable, or good tuning. So I could take a look at a flow controller, and I know what the range of tuning values should be for a flow controller. Same thing for a level controller, and so forth. And when I look at it, out of 5,000, only 1 in 5 are properly tuned. More shocking, 1 in 6 actually have default tuning. They're active, they're running. But in this example here, they actually have default tuning. That means they have never been tuned, never been looked at. They're probably running okay, because obviously someone would have looked at it. But when you think about it, they actually never been tuned at all. And 1 in 3 loops have suspect tuning, meaning that the tuning parameters are way out of whack as to what they should be based on that type of loop. And so that's why we talk about an optimization program, and what can we expect from an optimization? Well, all the good stuff here: more throughput, lower costs, and better quality, reduction of quality variations, and so forth and so forth. And so when I talk about an optimization program, we look at everything. We look from the process right up to, you're familiarized with the actual pyramid on the left side, and on the other side is sort of the path you would take to develop an optimization plan. So just a bit more about the Lakeside. Like I said, is generated from the Lakeside tuning index, and I actually rate the tuning from good to questionable to suspect. And I will actually even develop a dashboard for you. Some things I've talked about also, PV filtering could be an issue of measurement problem, and other nonlinear features such as I-deadband and the delta V could indicate a valve-related problem. So here's a dashboard that I would actually generate here. You can see here that this is the overall average, is the orangey red. You got suspect, questionable, and good. Now, in this example here, what really sticks out is the duplicate tuning. That means 2 or more control loops have exactly the same tuning. Does that mean, that's been tuned properly, or maybe it's just a copy and paste. Odds are one of those 2 loops, or 3 or 4 or 5, because I've seen multiple, like up to 5 loops have exactly the same tuning. One of those has actually never been tuned. You can pretty much guarantee that. In this example here, so you can see here, almost 50%, I think it's 45% of the loops had default tuning in this particular plant. That means they've never been tuned. And as a matter of fact, they actually recognize that we work with them with this dashboard. We work with them, and now I've actually been active, actually going through and actually tuning some of the loops that have never been tuned. This one here is an interesting one. Everything looks pretty normal except for this one right here. You can see here an excessive number, or well above average, of their PID blocks have excessive PV filtering. And then we are in talks with them as well, because we're suspecting that there may be some measurement issues. And that's why we try to hide the fact, we try to sweep it under the carpet. We try to hide the fact that we have measurement issues by installing excessive amount of PV filtering. This is a free service, so if you want to contact me, and we can talk about how we can generate a dashboard for you. I'm just coming up to the end here. My next session is March 13th, I believe, and we're going to talk about the P and the I and the D and what do they do. So we're going to go through actual proportional, and this will be interactive as well. So it's not just going to be any kind of just lecturing. We're actually going to have a live demo that I'm going to show you, where we're going to be able to make some set point changes and examine the effect of different P's and different I's and the dreaded D. You know what D stands for, do you? No, it does not stand for derivative. It stands for don't. It stands for doom, and it stands for disaster. So I hope you enjoyed this. We have a question period, and you're more than welcome to type in your questions. As I said, your questions are anonymous. I will read out the question, and I will answer them. And I look forward to have any questions. So please go ahead and type in your questions, please. And don't be shy. Now, like I said, I'll give it another few minutes. If you have any questions, if you think of a question afterwards, you're more than welcome to send me an email. I have some people razzing me right now, so I'm just going to give it another 30, 40 seconds if you have any questions. Yes, Josh, it is my birthday today. Yes, I am turning 39. As a matter of fact, I'll turn on my camera here so you can see I am turning 39. So, all right, I do have a question here. Is there any proper tuning for fuzzy logic controllers? Fuzzy logic controllers have fuzzy type of tuning. Honestly, I've actually never tried to tune a fuzzy logic controller, so therefore I'm not very familiar with that. I've never had anyone kind of actually properly explain to me how a fuzzy logic controller kind of works. I understand that it may be able to handle better nonlinearities. Delta V does have a fuzzy logic controller, but I'm more of a to be able to stick to something that I understand as well. Awesome. I've got some more question here. So I would appreciate if you can explain a bit about slew limit challenges in controllers, maybe in future sessions. I'm not exactly sure what that means. Perhaps, like I said, I'm not exactly sure what slew limits actually mean. If you can actually contact me directly, and we can maybe talk about it and be able to answer your question more specifically there. So these documents are available on the website. You can send us an email. Yes, we will be sending you a video presentation video presentation of this webinar. And another question, how often should loops be tuned? That's an excellent question. A lot of times what you should do is actually categorize the priorities of each loop. So let's say it's probably almost it's not even an 80-20 rule. Probably there's probably top 5 or 10% of your control loops that are critical, and other ones are important, and the other ones are not as important, I guess. And so probably a good idea to go and take a look at your critical loops on maybe a quarterly basis, to make sure that everything's operating properly, do some bump tests, document all the performance, because that way you can actually keep track. If there's any kind of changes in your process, you can keep track of it. So that's and then the other ones, and not, the important ones could be maybe a semi-annual, and then the remainder could be maybe on an annual basis. Excellent question, thank you. And that obviously that can be part of your optimization program as you actually go through your control loops. That's part of your optimization program, is to continuously take a look at this. Things degrade, things change, when we need to make sure we take a look at it. That is awesome. Any other questions out there? All right, I think I'll let it go for another 30 seconds, and then we will call it. All right. Well, that will conclude this webinar. I certainly hope to see you, or see you, or meet you my next webinar, which is, like I said, March 13th on PI&D. And I also have a basic instrumentation course scheduled for March 24th. I certainly hope to see you then. So thank you very much, and have a great day. Bye now.